Hey everyone, welcome back to my channel. So in today's video, we're going back to time series classification problem, but this time we're going to do audio classification. So our input time series would be an audio. Let me show you the framework for this project. So given a raw audio, we will do feature extraction with MFCC. And then we will calculate the distance. So we will do a classification using a distance-based approach. And that is done by ShapeDTW. And then after we get the distance between an input question with the reference, we will put that into a nearest neighbor and get the predicted label. MFCC is a topic on its own, so I'm not going to go into detail over this, but instead our main focus is ShapeDTW. Okay, so more concretely, we will study ShapeDTW and try to apply this to audio classification, even though ShapeDTW can be applied for any time series. Okay, let's study together. So ShapeDTW, we have two parts here, shape and DTW. The DTW part is dynamic time warping. It's the classical DTW. If you're already familiar with that, then it's the same. Maybe with just a little modification. And then for the shape here, it means that ShapeDTW tries to incorporate the shape of the input time series. Okay, so more concretely, for the shape part, we will get subsequence from each input and take the shape descriptors that we will denote it as T. And then for the DTW part, it's like the classical DTW. So we create a matrix of distances between elements. So this would be an element-wise operation. Let's say that we have two sequences. The first sequence is of length 9, and then the second sequence is of length 10. And the matrix of distances that I write here would have the dimension 9 rows and 10 columns. After that, we will get the warping or the alignment and compute the distance between input sequences. ShapeDTW was originally developed for univariate time series, but it can be easily extended to multivariate time series. And this is what we're going to do. We will do the multivariate version of ShapeDTW. And why is that? Because remember in the framework that I showed you earlier, we will do MFCC first before ShapeDTW. So the input of ShapeDTW would be the output of MFCC, and the output of MFCC is a matrix of 2 dimensions. Each coefficient represents a dimension, so the total coefficient will be the total dimensions of ShapeDTW. I will illustrate ShapeDTW using univariate time series first, and then later we can see how we can extend it to multivariate time series. Okay, now let's look at more detail of the shape in ShapeDTW. So basically, ShapeDTW's main goal is to improve the classical DTW by incorporating the shape. And so they try to align the sequences by looking at the shape first. More concretely, they do that by 2 steps. Actually, we already see this previously. So let's say that we have this input. We first take the subsequence, and in taking the subsequence, we have the notion of subsequence width. Okay, so let's say that we have a subsequence width of 3, and we are at the first time step. That means the subsequence that we will take would be 3 values to the right and 3 values to the left, plus the timestamp itself. Okay, so the length of each subsequence would be twice the subsequence width plus 1. Notice that we don't have values to the right of the first element, right? That's why we need padding. The output of the first step would be a matrix. The total rows is the length of the input. So this will be called S for subsequence array or subsequence matrices. The total rows would be the length of the input, and then the total columns would be the length of the subsequence. As the little s here is for subsequence. And then given the matrix S, we should get the shape descriptor. And that is done by putting the matrix S into a shape descriptor function and then get D as our output. D is to denote the shape descriptors. So if S subsequence arrays or subsequence matrix has this dimension D, the shape descriptors would have the dimension length of the input as the total rows, and then the total columns of shape descriptors depends on which descriptor function we apply. Okay, so I won't write anything here. There are several shape descriptor functions that we can take. The simplest one is raw, because that means we just take the raw input as its own shape descriptor. But note that in this particular case, we're doing an audio classification. So raw itself, it's not so raw anymore, because the input of ShapeDTW is MFCC, right? So it's already a feature, so like a subsequence of features. The derivative here means that we will take a derivative of the input and get that derivative as our shape descriptor. The derivative function would be derivative of each point in the subsequence, and the formula is exactly the same as in derivative dynamic time warping or DTW. I've already made that video, by the way, so you can check that out if you want to know the function. And then slope and HOG. HOG stands for histogram of gradient. These three actually, so derivative, slope, and HOG1D works with the same intuition. So they try to look at the shape by looking at the derivative or the slope of the sequence. And then the other two are PAA, which is piecewise aggregate approximation, and DWT. Don't mix this up with TTW though. So DWT is discrete wavelet transform. And the last descriptor function is compound. So with compound, we use combinations of shape descriptor functions. So the descriptor functions that I've mentioned above here is roughly divided into two classes. The first class uses more of the slope instead of the magnitude of the subsequence, and the second class is raw PAA and DWT. They fall into the same category because they try to look at the value at each subsequence. So we usually do a combination of like a mix of these two classes. In practice, we will put each shape descriptor into a list. That is if we want to use compound descriptor function. So at the end of the shape vase here, we would get a shape descriptor, which is a 2D matrix. And again, this is for one time series, univariate time series. Now, taking this 2D matrix, we will do dynamic time warping. So, well, the dynamic time warping, in short, is about finding the best alignment so that the sequence distance would be minimized. And as I just said, the input to DTW this time is a matrix of 2 dimensions. So, because we want to calculate the distance between two univariate time series, that means we would have 2 matrices. This is actually the same, let's just assume that these two have the same dimension, okay? All right. Actually, the dimensions of these matrices doesn't have to be the same. The total rows can be different, but the total columns have to match. Because the total columns in each matrix represent the dimension of the descriptor function output. And actually that can be guaranteed to be the same, because if we must use the same descriptor function for each input sequence. So the total columns of these matrices, the output of the shape vase would be the same. But the rows represent the length of the input. So if we have unequal length of input sequences, that's fine. The total rows of these matrices would be different. That's okay. Okay, to do this, we make another matrix that is going to cover the distance between each element. Wait, let me. Okay, this distance matrix would be a square matrix. Again, the distance matrix would be square if the total rows in both matrices are the same. But in general, that doesn't have to be the case. In general, we can have a rectangle distance matrix, a pairwise distance matrix. So for example, the first matrix has 10 rows and the second matrix has 5 rows. Then the resulting pairwise distance matrix would have 10 rows and 5 columns. After that, we will do the warping. So warping is about finding the best alignment. And in DTW, usually we have several constraints. The base constraints are, well, I'm going to show you. We have 3 base constraints. The first one is about the boundary condition. So the first element of the first sequence should be paired with the first element of the second sequence. And the same goes for the last element for both sequences. And then for the second constraint, it's about continuity, or sometimes it's called symmetric continuity. So this constraint is to make sure that we keep going with the time index. So visually, we can have alignment that looks like this. So the index in the first sequence is paired twice. The first pairing is with this one. Let's say that this index is A, and the second one is with A star. And then the third constraint is called monotonicity. Visually, we don't want alignments that looks like a cross like this, because that means the first pairing here, the first warping would be, for example, A and then B, and then the second pairing would be A star and B. I just realized that I write A for the black sequence, for the top sequence now, instead of for the bottom. Hey, sorry about that. Anyway, this means A star minus A would be bigger than 0, but B star minus B would be less than 0. And that's not allowed by the constraint of monotonicity. And then another notion in DTW is about step patterns. So step patterns is about where you can go in while traversing the distance matrix. The distance matrix between elements in shape descriptors. Okay. There are several very common step patterns. Probably the 2 most common is symmetric 1 and symmetric 2. And then the bottom right here is Rabin-Zhuang step pattern. There are many types of Rabin-Zhuang step pattern. This is of type 4 that is particularly shown here. Usually, well, some packages use symmetric 1 by default and some use symmetric 2 by default. In practice, well, in the code section later, we will see that we use symmetric 2. So after we find the path, so let's say that we go diagonally and then vertically and then horizontally, we will compute the weight, we will sum up the weights. And that's going to be the distance that represents the distance between 2 shape descriptors and eventually between two input sequences. Okay, now we're ready to extend the univariate ShapeDTW to multivariate ShapeDTW. Okay, with univariate we have one dimension, and with multivariate, let's say that we have 3 dimensions. Okay, we will have more in the coding sections, but anyway, so for the shape vase, taking the subsequence and get the shape descriptor, both univariate and multivariate works the same. Well, for univariate, we just do it once for one dimension, but with multivariate, we do it for the total of dimensions. We do it 3 times in this case. So let's say that we have this subsequence. Our subsequence would have 3 dimensions, and then the shape descriptor would also have 3 dimensions. The difference is with the DTW part here, because the warping can have can be applied independently for each dimension, or we can restrict DTW to have one common warping for all dimensions. That's the biggest difference between multivariate DTW and univariate DTW. Okay, so if you want to know more about ShapeDTW, you can refer to this paper. In this paper, they also show you how to apply ShapeDTW in univariate and multivariate case. Okay, so now here we are in the coding section, but before we go into the coding, let's look at the data first. The data is from Kaggle as well. It's about bird sound. This dataset only covers 5 species: Bewick's wren, northern cardinal, American robin, song sparrow, and northern mockingbird. Each recording has 3 seconds, so they have the same duration, and the sampling rate is 22,000, so 22,050 to be exact. And so we have 2 kinds of data. The first is the metadata, CSV, so this is about the details of the recording. And then the second type is the wave files. Here we have the recording here. Okay, so now let's look at the code. So first of all, to implement ShapeDTW, we're going to use ShapeDTW library. This is the extension of DTW library. Okay, next we will import some libraries. This time we import quite a lot. So the first group is of course the basic, like NumPy, Pandas, Matplotlib. PTS color palette is my own utility script, by the way. It's for color palette. And then librosa is the library that we're going to use to implement MFCC and loading the audio files. And then IPython is to allow us hear the recording. Okay, and then for this group, it's for applying the ShapeDTW. We will implement it step by step. Okay, and I'll show you why in a moment. And then we also need DTW function from DTW library. So when it comes to DTW, the very first implementation is for R, and then it has the Python version, and this is called DTW. Okay, and then the next imports are, well, if you're familiar with machine learning, this should be very familiar to you. Label encoder, and then turing test split, and confusion matrix display, and accuracy score. This is for knowing the performance of the model. And then the rest of the libraries are quite miscellaneous, but would be very helpful. Okay, so yeah. So in total we have, we have 9,000 recordings, but not all of them have the metadata. So let's look at the metadata here. The metadata has 5,000 recordings only, 5,054.22 recordings to be exact. So we will only look at these recordings which have the metadata. Okay, we will ignore the rest, 4,000 recordings. Okay, and then this cell is to look at the distribution of the recordings. We can see that Bewick's Wren have the most recordings, while Northern Cardinal have the fewest. But in my opinion, I wouldn't say that this is an imbalanced classification problem. Of course, there is an imbalance here, but it's not so severe. Okay, let's move on. So the next two cells are for visualizing the wave sound. Okay, so the first 4 rows are for American Robin, and then the next is Bewick's Wren, and then Northern Cardinal, and then Northern Mockingbird, and the last one is Song Sparrow. We can see that the bird sounds appear in different places. For example, like in Song Sparrow here, some recordings only show the sound at the beginning, and like in the 4th subplot here, we can see the sound, sort of like seeing the sound at the middle of the recording. So this is why ShapeDTW would be very helpful, because they can align the shape instead of aligning based on time index or I don't know, by something else. Looking at the index, looking at the shape is really important. Okay, now if we want to hear the one of the bird recordings, this is of Bewick's Wren, by the way. Okay, we can. Yeah, so that's the sound of Bewick's Wren, and this is the wave plot of that sound. Because it has a white noise, I guess that's why it has this this part here, and then the peak is when the bird makes its sound. Now let's convert that wave file into numerical data. To do that, I have to collect the file path for each recordings that have metadata. And so this is one example of the file path that we want to load using LibRosa. Since the duration of the recording is 3 seconds and the sampling rate is 22,050, the length of each file, each recording would be 66,150. So that's going to be the length of the raw audio. Okay, so our data, combining the validation and the training data, would be a 2-dimensional matrix. This is the total recordings, 54 to 22, and this is the length of each recording. Okay, now let's create the labels. So we take the labels from the name column in the metadata. I haven't shown you the first few rows of metadata, right? So let's see. So here we have the name column, and that's what we're going to take to make the label. But then the label would be of string, right? Whereas in machine learning, we need numerical. So that's why we need to encode the label using label encoder. And let's see the classes. So we will have class 0 refers to American Robin, and then 1 to Bewick's Wren, and then 2 to Northern Cardinal, and then 3 to Northern Mockingbird, and 4, the last class, to Song Sparrow. So the classes are sorted alphabetically. Okay, so that's the little pre-processing with the raw audio. And now let's go to the next stage, which is feature extraction of raw audio using MFCC. First of all, let's see how MFCC works with one data. So we apply MFCC using librosa.feature.mfcc, and then we have to type this y equals to put in the data. Let's say that we want to take the MFCC of the first data, okay, and then the sampling rate. And there are some other default values that might influence the MFCC result, but I'm just going to go with the default values for now. The hyperparameters are like hop length and then NFFT. I'm not going to discuss those hyperparameters, but yeah. Oh, and one important hyperparameter is the total coefficients. So by default, the total coefficients would be 20. So this picture here is of 20 rows. More concretely, MFCC, the variable MFCC here, is a matrix of 2 dimensions. The total rows is 20 and the total columns is 130. And that has something to do with the hop length. So in the context of ShapeDTW, let's just take as it is that we have a time series of length 130 instead of 66,000. So judging from this graphic, we can see that we have 6 very different rows, well, roughly around 6. The bottom one here, 1 and 2, 3, 4, 5, 6. Each row represents coefficients in MFCC. So because of that, I'm going to take just 6 MFCC. No, sorry, I mean 6 coefficients. Well, you see, each data generates 2 T matrix. So if we have more than one data, that means our final output would be a matrix of 3 dimensions. And we will store that as MFCC's all. So we are expecting to see MFCC's all.shape to be a tuple of 3 values. Okay, so the feature extraction is done now, and the output of that is just as we expect. 5422, this represents the total recordings, and then 6 is for 6 coefficients, and 130 is because of the hop length. Actually, 66,000 divided by the hop length. Let me show you. So 66, that is the shape, the total column in data divided by hop length. The hop length is 512 by default. See, 129, a bit over that. So it's rounded up to 130. Okay, now, well, this cell is just for showing you again the MFCC visually. Since we have 6 coefficients, now we have 6 rows only in this graph. 1, 2, 3, 4, 5, 6. Okay, now we're done with MFCC. The next step is to put this into ShapeDTW. But before that, we need to split the data first into train and validation. Sorry, this is actually train and validation. Okay, and I set the the validation data to be 20% of the whole data, so that we have around 4,000 4,000 recordings in the train dataset and around 1,000 recordings in the validation dataset. Okay, this cell is just to ensure that the class distribution in the train dataset is similar as in the whole dataset. And yeah, it looks okay. It looks quite similar to this one. This one, okay. Yeah, now let's move on to ShapeDTW. Okay, so for ShapeDTW here, I'm going to show you step by step. And for this particular example, I'm just going to use the 7th recording, index 6 and 7. First of all, we take this subsequence, right? And that is going to be done with multivariate subsequence builder. By the way, the subsequence width is 3. And then yeah, we use the transform time series to subsequences method. And we name it as subs and subs1. And then we put the subsequences to get the shape descriptors. We use raw subsequence descriptor, by the way. I'm just using the raw one. I'll show you the result of using other shape descriptors. And then, yeah, so we need to get the shape descriptors for each subsequences. So I have D and D1. D is the shape descriptors for subs and D1 is for subs 1. That is for the shape vase, and then for the DTW vase, we have to calculate the distance matrix. We are doing the dependent version of multivariate shape DTW, so we have to apply the calc summed distance matrix method. Okay, and I'm just going to take that method from D and take D1 as the argument. Okay, and then put that into a distance matrix, and then using DTW function from DTW library, we take the alignment and the distance of distance matrix. Okay, so let's run this. So we can see that the distance, so we can see that the distance between train X6 and train X7 is 76,000. Okay. Actually, we can do all of this in just one function, which is shape_DTW. This is from ShapeDTW library. And with this function, we put in the inputs and then the subsequence width and the shape descriptor. This will get us the same result if we take the shape_distance attribute. But I'm going to show you later that it's not efficient to do that. So that's why I need to show you the step-by-step process. Okay, but the advantage of using shape_DTW function is that we can plot it. Again, we are using the dependent version of multivariate ShapeDTW, so supposedly the warping, like the alignment of all these subplots should be the same. But I guess the easiest one to look at is from dimension 2. So yeah, we can see these two sequences have quite similar shape, except for the tail of both subsequences. And we can see that the tail at the blue sequence, the bottom sequence, is quite similar to the shape of the tail of the top sequence. So that's why, the tail here gets a lot of pairing. Here we can see it too in dimension 3, that at the end of the blue sequence, the bottom sequence gets paired a lot with with many parts of the top sequence. Okay, we have gone through the process of calculating ShapeDTW between two sequences. Okay, so here the next step is to do ShapeDTW for all recordings with parallel computing. And to know why I have to do it with parallel computing, we need to step back a little bit. Okay, so KNN, K equals 1 in this particular case. Okay, because ShapeDTW is usually paired with 1 nearest neighbor. Sorry, not only ShapeDTW, but DTW in general. Anyway, okay, so let's say that we have our training data drawn here. Each color represents a class, and then we have a data in question here, denoted by X. We want to get the predicted label for this X, right? And to do that, we calculate the distance between X and each data in the training data set. That's for one data only. We have 1,000 data, 1,000 recordings in the validation data set, so we have 1,000 X's. And so to do that, to compute the distance between all X and all data in the training data set, we would need to take the shape descriptor for each data in this space several times. So this is why if we implement shape_DTW function, that means we're going to calculate the shape descriptor over and over, and that's going to be inefficient. So that's why I have to break down the ShapeDTW function and optimize it. So let's go to this slide. For the shape vase, we're going to get the subsequences and shape descriptors T just once. for all the data. Okay, and then for DTW, well, there's nothing we can do about it because each time we calculate the DTW, the distance it's going to be a different pair. So I will make two functions here. The first one is to get the shape face done, and the second one is to do DTW and predicting the label as well. So here, let's say, let's erase the inks first. Okay, let's say that we have the question here, and then the closest distance, the closest data to X would be this purple data, right? The class, well, because we know that it's purple, that's why we will give the the purple label to X. So the second function would get DTW, would get the DTW face done and get the label too. Okay, so let's look at the functions. So here, the first function is to get subs and subsequence and shape descriptors. This function is going to be applied on each row in both datasets, the train and the validation. And then this here is descriptor, and I'm going to set it by default to raw, which is already defined before. So this function will return the descriptors. Okay, and then given that descriptors, the second function is to find the nearest neighbor. So given a recording in question, we will compute the distance between that data with all 4,000 data, right? All the distances would be stored in a list called distances. And then, well, let's say that the closest data, so the smallest distance is in the 100th data. So the 100th data is the closest to the data in question, and so 100 is going to be returned by this function. Okay, so this data, I said earlier that the second function will get us the predicted label. No, actually not that. It will get us the index of the trained data that is closest to the data in question. Now let's get the descriptors first for all the data set. The first cell is for the train, and the second one is for the validation data. We can see that all cores are used. Now I put the rest of the section into KNN because, well, it's actually about finding the nearest neighbor, right? So I'm not going to run this cell because it's going to take 2 hours and a half. More than 2 hours. That's the only disadvantage of using ShapeDTW, because you have to calculate the distance for each pair of data. By the way, the parallel computing here might not be the best. I'm not good at parallel computing. I'm not good at optimization. So if you know better ways to do this, please let me know. Okay, back to the code. So in this cell, I want to compute the distance between each data in the validation data set with all the descriptors in the training data. So the idea is that each process would deal with different descriptors from the validation data set, but all cores or all process would have a list of the descriptors from the trained data set. All part of it, the whole descriptors for trained dataset. Let's look at the run notebook. I've run this before. The output of this cell would be closest, and this is the index of the training data that is closest to the data in question, as I said earlier. And so to convert that into the predicted label, we need to index train Y with the closest indexes. We can do this because we are just going to take one nearest neighbor. If we take 2 nearest or 3 nearest neighbors, it's going to be a bit more complicated, because if we take, let's say, 3 nearest neighbors, then we need to take the majority class in 3. So let's say that 2 out of 3 classes have the class 0. That means the class of the question, the data question would be 0. Okay, and then the next cell is actually just for, let me bring it up here. So the next cell here is just for like ensuring, this is one of my favorite way of looking how the model works. Because we're doing classification, I want to make sure that the predicted distributions, the distribution of the predicted class is roughly similar to the original data. And judging from this bar plot, we can see that it's quite similar. Okay, so yeah, I'm going to cover the confusion matrix first, okay. But this cell is, to make the confusion matrix, we're using from predictions method. And I also put the accuracy score as the title. Okay, so yeah, here it is. The accuracy is 93%, 93.179, 93.2%. Okay, so yeah, not bad. I've seen some submissions on this particular dataset that can achieve 97.7%, but that's using convolutional based classifier. So I think when it comes to distance-based classifier, ShapeDTW has achieved a very high accuracy. The biggest misclassification is recognizing northern mockingbird as American robin. Recall that these predictions can be achieved by using raw descriptor function. I'll show you the result when we use derivative shape descriptor only. So all other hyperparameters stay the same except for the shape descriptor. So with derivative shape descriptor, we achieved 89%. And then I also tried using both of them. So raw and derivative. Raw and derivative. Oh yeah, by the way, if you see here, cancelled after 12 hours. This is because I'm using the shape_ttw function. So back then, I already have a hunch that this would be inefficient and would take forever, but I just tried it anyway, and yeah, I got nothing. So yeah, because because the session limit is 12 hours for Kaggle notebooks, so yeah, after 12 hours. So if after 12 hours we still haven't finished running the codes, the session will be cancelled and no notebook is published. Okay, so in the next session, in the next version, I use compound descriptors. I use two descriptors, the raw and the derivative shape descriptors, and using the parallel computing that I already described. And we get 92.9% of accuracy. So that's slightly lower than using only the raw shape descriptor, even though we get less, only one fewer misclassification for song sparrow and pewix wren. But I thought because using a raw descriptor only can get higher accuracy, that's why I show that first and show that as my final version. Some other modification that I tried is increasing the coefficients in MFCC and change the stop pattern. So stop pattern in DTW. I haven't told you about that, sorry. So the stop pattern used in this particular project is symmetric 2. So recall that by default we use symmetric 2 stop pattern, but I tried to use stop pattern 1, symmetric 1. So there are two modifications here. First, I increase the coefficients in MFCC, and the second one is I change the stop pattern. The accuracy is 93%. Oh, honestly, we get fewer misclassification here. So perhaps increasing the coefficients in MFCC to work. I didn't try changing the stop pattern into symmetric 2 again with 10 MFCCs. So yeah. I'll put this notebook in public so you can download it. And if you want to try it, modify the hyperparameters. Let me know if you can get a higher accuracy score. I mean, like, let me know the hyperparameters that you use. Okay, so that's it for today's video. We learned ShapeDTW and applied for audio classification. If you enjoy the content of this video, please consider subscribing to my channel, Timely Time Series. Don't forget to share and give it a like, and comment down below what you think about this video. And I'll see you next time. Bye bye.